you can just take in from the chat. Again, explain that and past. So we'll carry forward. So Symbian OS. So this is the overview actually. So how Symbian OS is ported to ARM processors is like it's very finely tuned on ARM processors. So you know ARM is a architecture which we are generally using for embedded processing. So it's very a low controller device, low power consumption device actually. So it consumes low power. So you know you are using a mobile device, and that consumption is the most important thing. So ARM processor is basically designed to operate in a low power consumption mode. So ARM processor will have some instruction sets, and we need to port that Symbian OS to the specific ARM architecture. So basically Symbian OS is portable to the ARM architectures, and it is finely tuned with ARM architectures. We can use that processors. So most of the Symbian OS uses ARM processors, which are widely used among 70% of devices. Like before this Android came, we have Nokia phones, right? So we don't have smartphones like now we have Android OS, which is using internally Linux kernel. Okay, so previous to that we have Symbian OSs, which Nokia heavily uses that Symbian. So Symbian is a product of actually Nokia only. So yeah, so this is Symbian application architecture. So it provides the APIs for the buttons, voice features such as hands-free speaker phones, and we can also make conference calling. It also have a conference calling capabilities. So application views, we can create application views. We can use application engines, powerful development platforms, and we have a good GUIs within the Symbian OS. Okay, so it will provide a good graphical user interface. It will provide that. Symbian OS provide that. So application development tools. If you talk about application development tools, so it will support your Symbian C++ software development kit. So Symbian will have its own SDKs. So if I want to create some application on my Symbian OS, then we will have Symbian C++ software SDK support within the Symbian OS. So by using that SDK, we can create applications in C++ and we can run in Symbian OS. So it also supports one Symbian emulators to see whether my application is actually working on my hardware. So it's like emulator is nothing. It's emulation of your hardware actually. So emulator, you can use your emulator on like most machines. You don't have your target, right? You don't have your embedded device. Now you want run and you want to check your software running perfectly, or whether it's compiled, that binary is compiled perfectly for your architecture, not it's working fine or not. So what you can do, you'll have some Symbian emulator. It's a software which we can run on the host. Just it will work as it is working on a target. So it will actually emulate all the things within the hardware, in the software layers. So you can actually see my application running on host, which are basically compiled for your targets. Okay, so Symbian also supports your emulator for applications development using Windows, Matrowork, and so code. So Code Warrior, Windows Matrowork and Code Warriors. These are some tools which it will use. Emulator will use for running your images which are built for your target. But we can run on those host machine by using this Symbian emulators. Okay. So it also supports synchronization. Like synchronization, it supports sync ML synchronizations, synchronization softwares. Yeah. So Symbian OS. What are the basic functionality of this Symbian OS? So the basic features, basic functionality of this OS is like, it will take a low boot time. So you know what is boot time? Boot time is when we power on your device, how much time it will take to load your OS from somewhere in ROM or in flash memory, to take that, to put it into the RAM and then execute it, give it the control to the controller, to the CPU, and it will execute your OS is nothing. It will run from your RAM only. So it is the time taken by the OS to load itself from ROM or your flash memory to the RAM memory, so that it can execute with the CPU. That is actually your boot time. So there are lots of constraints in the boot time. So there are companies which are working hard on how to reduce the boot time of the operating systems, how you can actually minimize the boot time of an operating system. So you know, like Microsoft is working very hard. Like you have Windows 8, you have Windows 10 now, so they, within seconds you are able to boot that machine, right? So if you have low boot time of your OS is good, and you are able to run your applications quicker and faster. So this Symbian OS also supports multiprocessing, multitasking, and multi-threading, and there is one term, multi-programming. So I will briefly explain you what all these terms are. Basically, this is the OS jargon actually. So you should be clear about what is these things: multitasking, multi-threading, and multi-programming. So Symbian OS supports all of these. Symbian OS supports all of these. So we will be discussing these things one by one. First, I'm taking multiprocessing. What is multiprocessing? Multiprocessing is kind of like, if I have more than one core of CPUs. Okay, if I have 4 cores, so I can run 4 different programs, 4 different processes at a time. If I have multiple cores. Okay, so that is called multiprocessing. I have more number of CPUs and I can run all those processes parallelly, because I have 4 number of CPU cores. Okay, that will increase my performance. And so in that case I need to have multiple processes which are there in the RAM. Okay, if there are multiple processes which are ready to be run in the RAM, then they can be processed by 4 cores. If there are 4 processes, they can be run by 4 different cores. That is multiprocessing. It usually related to your hardware. Then multitasking. What is multitasking? So before multitasking, I will be explaining you what is multi-programming. Multi-programming is in like, you have multiple programs. You have multiple programs, you have multiple processes in the RAM, but you are running a single program at a time. Okay, there are multiple programs, multiple processes which are waiting to get the CPU resources, and which are there in the RAM. They are just waiting in some wait queues. They are waiting in some ready queues. Okay, you have some like schedulers, long wait schedulers, short-term schedulers, long-term schedulers. They will actually schedule your ready queues, and they will be you will be getting your process will be waiting in that. If it is not getting the CPU, if some other processes is running, those processes will be waiting. But you have multiple processes, multiple programs in memory. Okay, so this is called multi-programming. We are creating multiple instances of programs, multiple instances of processes, then but we are running single instance at a time within the CPU. Okay, so this is your multi-programming. Then we come to multi-threading. Okay, we'll come to multitasking first. So multitasking is like, you have I'll just tell you what is multitasking. So multitasking is like, in that case, in multi-programming case, when one process or one program is running, nobody will interrupt that, actually preempt that. So it will run until it finishes. Okay, or it voluntarily preempts itself, or it will voluntarily go for some IO operations. Okay, voluntarily, if you want to release the CPU, it can go and take some if it is waiting for some IOs, it can wait for that. And then from the ready queue, we will pick up some another task. We will pick up from another process, we will run that. Okay, but in this case, in the multitasking case, what is there? We are having CPU time sharing slots. CPU time sharing slots. So if I'm giving some time slots to each of my programs, to each of my process, so each of my programs or process which will be assigned with some slots, some CPU time slots. So once that time slots will be completed, your scheduler will schedule another task. Once that time schedule is some completed, your scheduler will schedule another task. So it's kind of, we are giving a fair share scheduling timing mechanism to all the programs. So it's called multitasking. So we are giving a parallel kind of parallel running kind of feeling to all the processes. They will feel like we are getting all the time of CPU, but the time is very short actually, and your CPU is running at very high frequency. And if the time is very short, all the programs will feel like we are getting the whole amount of CPU. Okay, so it's kind of parallel programming we are doing. Okay, so, and we need that actually, because if we want to run so many processes at a time, then we need to give some kind of mechanism, like we will give some time slots, and then for that time slot one process will run, for that time slot that process will run again, the cycle will run again. Time all the time. Okay, some time slots all the time. So this is called multitasking. Now we come to multi-threading. Multi-threading is like so multi-threading is very important concept. Multi-threading is important in the way, like if we I will give an example, like if I have some game and I want to if in that game, like some balloon shooter game is there, suppose some balloon shooter game is there, and I want to design that game, and what I want to do, I want to show the I want to show the score also. I want to show how many balloons were shooted, how many balloons were left down, and I want to show the graphics of the graphics of that game also. Okay, so these are kind of 4 or 5 tasks. So these tasks I want to do at a time. Okay, and these cannot be run sequentially. Okay, sequentially I cannot run this thing. If I will create a program sequentially, if I have some function call sequentially, that will not achieve my purpose here. So what I need to do, I need to create some dynamic execution threads within the same process. So if I'm creating within the same process some different dynamic threads, I will create some threads which are dynamic in nature. Those threads are lightweight process actually. They will be using the same code, but they will be having their own stack pointers, they will be having their own program counters. So dynamic execution of those threads will be different. Okay, so in that way we are actually achieving running parallel task, parallel dynamic execution from the same application itself. If I have this one game and I want to execute 4 or 5 features within that game, I have to create 4 or 5 multi-threads, multiple threads. Okay, I have to create threads for it. Then only I can achieve that game functionality. It's very important concept actually to gain your application. Your application, if you want to work properly, you need to do that actually. Okay. So I have explained you about multiprocessing, multi-threading, multi-programming, and multi-tasking. Let me know if you have any questions about these things. I will be giving 2 or 3 minutes of time to you because this is important concepts. You can write your questions on your chat if you have any questions, query related to these forms which are heavily used in the OS. Every OS they use that actually. We'll be, okay. Okay, I'll be waiting for 1 or 2 minutes more so that if anybody wants to ask some questions, otherwise we'll be going ahead. So I think you're getting something from this thing. Okay, so we'll be going ahead with our presentation. So next, the Symbian OS, this also supports your processing, multitasking, and multi-threading. As I already explained you about multiprocessing, multitasking, multi-threading. So now it also supports your internet connectivity. Internet connectivity in the sense it will support your web browsers, and it will support your IP-based network connectivity and Wi-Fi that will be supported in later versions of Symbian OS. So since you're using your mobile phones to make a call, it will definitely support your cellular GSM and CDMA phones. So GSM is global system for mobiles and CDMA is code division multiple access. So these are two techniques which we are using for cellular phones, to work with cellular phones, to make connections or to talk to some other phones. We will have GSM and CDMA technologies within the phone integrated, within the Symbian OS integrated, so that they can be used for making the calls. So next is the memory support. How much memory we are actually supporting in Symbian OS. So there is large amount of memory supported as compared to Windows CE and Palm OS, which we have discussed in the last session. So it supports 80 MB of built-in memory, and that will be supported through multimedia card. So MMC card. So MMC card is your like you have some SD cards which you can actually externally you can replace that and you can insert that anytime. So it will support 80 MB of built-in memory. First of all, it will support 80 MB of built-in memory, and it can also support your external MMC cards, which are called SD cards. So SD is secure digital memory cards, and the communication between SD card and your controller, that will be doing with your secure digital input output protocol. So your SDIO protocol, secure digital input output protocol, that will be a protocol will be used with your memory card and your CPU to communicate the data. So SDI is a protocol. So Symbian OS also supports functionalities, additional features, security features like RSA tokens, like MD5, and many other additional features. Like it's standardized. It uses standardized APIs for high resolution screen. So these are the supports for the Symbian OS. So standardized APIs. APIs are programming interface. So those are some functions which will be used for this designing the high resolution screens. So it will also support non-volatile file systems using flash memory to save the files, and instead of saving them in persistent battery backup RAM. So as you know, in last session I told you about persistent battery backup RAM. So there we are actually somehow managing your memory data will go off. So if you have battery backup RAM, uh, your memory can be saved in the RAM itself. So it's kind of persistent battery backup RAM. But in Symbian OS, instead of battery backup RAM, we are using you're using flash memory. So flash memory is a non-volatile memory. Okay, there is no need of battery backup here in the case of flash memory. It's a non-volatile memory. So it supports a non-volatile flash file system. You know, file system, what is file system? File system is kind of like, you know, FAT32, ext2, ext3. So these are file systems. File systems means you have some how you are actually managing your files and directories within the partitions of your memory. Okay, you got some hard disk. Now you create some partitions. So when you do formatting, you are actually creating some kind of structures, some kind of arrangement to arrange all the files. Okay, so yeah, so from because when you're calling from an application side, you should that structure is actually having the information of all the files that are kept within the hard disk, that are kept within the partition within the file system. So that's the reason why when you're calling some file from your user space, you are able to achieve that file because it is creating some inodes structures information. Okay, So instead of saving them in persistent battery backup RAM. Yeah, so this is the file system. So Symbian supports the ARM processor, heavily supports the ARM processor, for ARM processor, which provides sufficient code and energy. So I already told you, like ARM processor, energy efficient processor architecture, low power consumption device. So and there's a high efficient called thumb instruction set. So thumb instruction set, it's having good code density. We are including that set to increase the code density. Maximum number of code in the sense the instructions which we can actually store in your RAM. Okay, so that code density is it's more actually. Okay, if some instruction is less than 16 bits. Okay, so there is nothing, no sense in allocating 32 bits over there, right? So normal ARM architecture is 32 bits, but the another set of feature is 16-bit mode. So if you go in 16-bit mode, you can actually use that 16-bit mode to to combine two instructions. Two 16-bit instructions can be combined within the same 32. So that's how you are actually able to reduce your memory footprint, and code density will be increased, right? Yeah. So yeah. So what all software it needs, it uses actually. So it for the desktop it uses Lotus and Windows programs, and it also uses graphic support, including support for 3D rendering. So your CPU is used for processing, and when you want to process some graphic related stuff, we have kind of GPUs, graphical process units. GPUs are used for like digital signal processing, image signal processing. They will process your image, and then they will render the graphics image on display. So that work is being done by GPUs. So it also supports the softwares for GPUs. This Symbian OS also supports the software for GPUs, so that you can display anything on your LCDs or on your LCD phones, like you're using some LCD handheld devices, right? So yeah, it supports APIs as compared to Windows CE, your personal information management phones. So it supports all the APIs as compared to Windows and your Palm OS and Java phones and all those things. And it also supports telephony standard interfaces. Okay. So it also supports mobile information device profiles, and then sync ML, synchronization, contacts, office, address book, spreadsheets. These are all the applications which are actually supported, like calendar, agenda, word processor, text to speech converter, browsings, your browsers. So it supports your messages like SMS, MMS, email, all these things on map, your Microsoft Office formats. Also it can support. Okay, development support on C and C++ and Java platforms. On Java platform, because it is also supports Java application SDKs. So GUI application development, I already told you about, will support in all the three languages. It will support in C, C++, and in Java. So for Java, we have some separate standard like Java edition. So Java for mobile editions like J2AC and J2, we have J2AC like Java 2 standard editions. Similarly, we have J2ME for mobile editions actually. So we will be creating applications within Java language, but there is a different set of APIs with a different set of SDKs which we are using to create the applications specific for mobile embedded devices, for mobile operating systems. Okay. Multimedia applications such as playing musics, and then it also supports wireless communications through WLAN. So WLAN Wi-Fi chipset it will be supporting, and then we can also support wireless communications, Bluetooth and all those things we can support here. So for like Adobe Reader, Adobe Reader, like PDF Reader is Adobe Reader, which is used for accessing PDF files. It also supports the Adobe Reader, and then cementing client security for like antivirus support is also there. And so this is not that useful. So it also supports BlackBerry, your Connect, Oracle. These are some specific to Symbian OS, BlackBerry Connect, Oracle collaboration suites, secure mobile connections via VPN clients, and all those things. Yeah. So those are all the softwares which actually supports for Symbian OS. Now we'll come to ports. What all ports this OS, Symbian OS supports? Yeah. Any questions as of now? Any question from that side? Okay. So your USB ports and your infrared, your telephony ports. So telephony in the means of like GSM, your CDM, I already talked about that. So telephony, it supports those things. And for Bluetooth communications with mobile phones and external modems. So it will support your Wi-Fi, your Bluetooth, your infrared, your serial USB. These are all the protocols actually. So to communicate between something. So serial communication we can do USB communication, we can do Bluetooth, and it supports all the protocols. So it should the Symbian OS should support the stack for these things actually. Okay, the protocol stack is software layers. So serial will have some set of layers, Bluetooth will have some different set of layers. Okay, so we will not go into that detail for the stack layers. So it will support some drawings, preparing slideshows. So these are all the softwares it can also support, so that we can actually enhance the functionality of your softwares, and we can run more number of applications from third-party vendors. So application layer above the Symbian with OS. So now I'm like telling about you how the layers, how this layer is designed. So at the top layer, there always be an application layer. For every OS, at the top layer, there will always be an application layer which will be running in your user space mode. One is your kernel space mode, one is your user space mode. So as you should know as of now that OS and of your abstraction layer, we don't want any application to directly talk to your hardwares, right? If I have some hardware like Wi-Fi chip, Bluetooth chip, and I have some your keyboards, your mouse, your CPU, your all these your hardwares, right? Your MMU, your RAM. We don't want our application to talk directly to the hardware. So because we want to efficiently use the hardwares. To efficiently use the hardware, we definitely need some kind of software which will manage all the CPU resources, all the RAM resources, all the interrupts. Interrupts are also the resources which will be generating by your APIC, Advanced Program Controller interrupts. Okay, I'll be covering the interrupts after some time. Symbian uses interrupts to execute their applications. Okay, so yeah, that is why that is what the reason why we're using OS, so that we can efficiently use the memory resources of the hardware, memory resources, and efficiently use the hardware to run more number of applications. Okay, so at the top layer we will be having application layer, and then in between we are having this OS, Symbian OS. So Symbian OS, the main part of the Symbian OS is the kernel. For every OS we have kernel is the main part, main core. So that will be contained in ring 0 is the main center of the OS. So basically what the functionality of kernel is like, it will take care of your memory management, how memory management will be doing process management, it will create the process, it will schedule the process, it will allocate the memories for the process, and it will handle your interrupts from the devices. So it will also do interrupt management. Okay, it will also manage your networking, it will also manage your file systems. These are the five basic things which will kernel will actually do. So kernel will do your process management, memory management, it will do your file system management, networking, and it will do your IPC also, inter-process communication between the processes. How different functionalities, process to memory, memory to process, it will communicate. So those will be communicating with some form of communications. So that are called inter-process communications. So like we have semaphores, mutex, we have some message queues. Mutex is not inter-process communication. Mutex is locking mechanism, actually synchronization mechanism. So so these are kind of like features we are using in the kernel. Kernel is the main part to all the things. So you know this memory runtime story, data encryptions, and security, some encryption features like SHA, RSA, MD5. These are encryption algorithms. SHA, RSA. These are encryption algorithms. To manage the security, we need to encrypt the data, and at the receiver side we will decrypt the data from the same algorithm which we have designed previously. So it supports the security mechanism also. And then inter-process communication, I already told you about, on events, messages, and all these things. Communication APIs for HTTPs, TSP-IP protocol for your IP networking, IRDA for your infrared, multimedia, images, graphics, CDMA technologies for your cellulars, GPRS, GSM telephony. So all these technologies it will manage in your kernel. Okay, all these functionality should be there in your kernel. These are some subsystems, kind of, you can say. Then below that kernel you will be having your hardware. So hardware, so hardware in the sense we will be having ARM processor. So ARM processor, you'll be having ARM CPU, and with that we will have some display, we will have keypads, modems, Bluetooth, IRDA chipsets, USB chipsets, USB controllers, Wi-Fi chipsets, radio transceivers to receive and transmit the radio frequencies. Because Wi-Fi and Bluetooth works on radio frequencies, so we definitely need some radio transceivers for that. So for Bluetooth, so it will work with Bluetooth, your IRDA. Bluetooth and IRDA will create your WPN networks. So WPN is wireless personal area networks, and your internet works with TCP/IP protocol suites, and then your mobile device works with GSM and CDMA phones, and then your Wi-Fi works with MAC and PHY communications. So these are different communication protocol stacks which this Symbian OS supports. Okay. So yeah, these are the apps which for different technologies we are actually different protocols it supports, like WAP, your wireless access protocols, and then Wi-Fi, your CDMA, code division multiplexes, your GPRS, then your GSM technologies. It also supports our serial APIs, Bluetooth APIs, IRDA APIs, TCP/IP communications, and APIs for HTTP, TCP/IP, DNS, SSL, WAP, and PPP. So what is the summary? Summary is we have this Symbian OS which supports multi-threading. It supports multi-modal communication. That means it supports your image, your videos, your text, everything, your audios, and it integrates synchronization multimedia also, and it supports application development with 3 languages plus in Java supports. Okay, it is finely tuned with ARM processors. That means it can be ported to mostly to ARM processors. ARM processors are low power consumption devices, so we can actually use those for handheld devices. So Symbian OS is a handheld mobile. It can be used for telephony protocols like CDMA and GPRS, and and GSMs, and then network, Bluetooth, Wi-Fi, Ethernet, all these things, TCP/IP network protocol suites. So of this. if you have any questions regarding this OS. If anybody is having any questions regarding what we have just discussed about Symbian OS, we can take your questions because we have time. Okay. Okay. ARM processor full form. ARM processor full form. Somebody is asking about ARM processor full form. I'll tell you, ARM is your advanced RISC machine. Okay, it's your advanced RISC machine. So then you have some questions about RISC. You know what is RISC and CISC. So Intel architecture is basically your CISC architecture, and this is your ARM architecture is basically your RISC architecture. What is RISC is reduced instruction sets. Okay, we will be having reduced number or less number of instructions. The complexity within the hardware is more. Okay, the complexity within the hardware is more, so that it can actually process your instruction. So your instruction will have your instruction set will be less in that case, and your CISC will have complex instruction set. Okay, so yeah, so this is the ARM advanced RISC machine. ARM basically uses barrel shifters within the hardware. So what happens is like you suppose you have some machine, you have some operation. Yeah, you have some something like move E. So move A B, it will transfer your B data to your A data. Okay. So this is just a move operation, but if you want to left shift and right shift, if you want to divide and you want to multiply also, you can do within the same instruction actually. Okay, because you have the hardware capability. Barrel shifter will do that actually. So if you since you have the hardware capability, your instruction within your single instruction you can do multiple things. You can multiply, and then you can add, and then you can store the result, and then you can store the result in some memory location. That is what your basically your ARM processors designed for. Because we also want to reduce faster our operations. Okay, multiply, divide operation will be faster by using these barrel shifters kind of hardware mechanism in the ARM processors. Any other questions? So in this way, we actually in the last session we actually covered about Palm OS, Palm operating system, and then we discuss about Windows CE mobile operating system, and then in this lecture we have discussed about Symbian OS. So in this we have completed your whole mobile operating system chapter is there. So that whole chapter is finished now. The general OS and that previous thing, the general features of OS was being covered by another colleague of mine. And I think we have left with some time, so we can actually cover something which is left in Windows CE also. I'll be covering some part with Windows CE because last time we have some like network. Can you have any other questions related to Symbian OS? So I'll be answering your questions. So last time, okay, somebody is asking about nowadays which OS is used for developing mobile applications. This is from Jntuk. They're asking about this question. Okay, so nowadays we are actually using Android operating system. Android operating system is being developed by Google. They have acquired this Android OS and they are actually developing their Android APIs to develop applications over this Android. So basically Android, the kernel of this Android is Linux kernel. So they will be using Linux kernel, and above that they have Android framework, Android structures, Android layers. So in Android we heavily uses Java applications. So yeah, so it's very portable. If you generate some bytecodes in Java, that is easily portable to different architectures, and yeah. So we uses ARM architecture. ARM architecture is hardware, and Android OS is generally using for nowadays running applications for mobile applications, developing mobile applications. Symbian OS was uh, yeah. So somebody is asking about how Symbian OS is different from your Android OS. Yeah. So for this question is like your Android OS is it's supporting a very huge framework actually. It supports a large number of it supports your large number of APIs actually. It can support your Bluetooth APIs. It is in your Wi-Fi APIs, and it supports a large number of APIs. Okay, actually it supports your large number of SDKs, RDKs, PDKs. There are so many developers we can use here in Android, but in Symbian we are just using SDKs only. Okay, we are just using C++, and some applications we can put it in Java. But here, instead of using in C and C++, we are creating the binaries in Java. So Java internally, then framework will be having some C++, and then Linux kernel will having some C. So it's a huge, it's a big combination actually of C, C++, and Java applications will be faster enough to execute it. Okay, so and it also supports your multitasking, multi-threading, multiprocessing in a very efficient way. Yeah, algorithms here are efficient actually. The scheduling algorithms is also more good as compared to your Symbian OS. You can actually create your widgets. And the Android framework, your Android open source community is there actually. Symbian OS is not having an open source community, so people can contribute to that open source community. This is a if you know about Android is open source, so everyone can actually the developers from different locations contribute to this OS, and they can increase the functionality, increase the features of this. Symbian OS is not, it's a proprietary tool. Symbian OS is not Android open source. It's not open source. So yeah, so that is why Android is more popular, more famous, because so many developers were contributing to contribute some of the features that they know within this Android OS. So it supports a large number of devices. It supports a large number of features as compared to Symbian OS. Symbian OS is very old now. Any other questions? Um, at in the previous session, we are left with some of the concepts within this Windows CE. So I'm covering this this part here because we have time around 20 to 25. Okay, so we'll be covering this as of now. Anybody's having some questions, or we can go ahead. This is Windows CE part 2 we are left with actually previously. Okay. So your Windows CE is also a mobile operating system, but here we have this is how the application layer fits here. So you will be, so since Windows CE, I already told you this is a proprietary of Microsoft. So Microsoft not open source. They will keep their source code with themselves, and they will give you binaries. They will give you the executables. You can run those executables on the Intel machine or in some other ARM processors or something else. So this is how your Windows CE stacks looks like. So at the bottom layer, you will be having your hardware that is similar. Hardware, that means your CPU, your memory, your firmware pens, your keypad, your touch screens, your Wi-Fi device, your Bluetooth chipsets, and things, which will be communicating at the lower need with the protocol stacks like Bluetooth stacks, TCP/IP stacks, GSM CDMA for telephony stacks, and they will be accessing to the networking technologies like WPN devices, internet and mobile services, networking providers. Above your hardware layer, you will be having some Microsoft source code for assemblers, and that will work as a hardware abstraction layer. So in this Windows CE, we have some extra layer that is kind of abstraction layer above hardware. So we are not having directly kernel here. We are having some abstraction layer. We are using the hardware abstraction layer here as some another layer. So kernel itself is not directly communicating to your hardware. In the case of Symbian OS, kernel is directly communicating to this actually. Okay, and then above kernel we are having your kernel features. Okay, kernel features. So it's kind of different. This whole Windows CE is divided into some layers. So first layer is memory management, your process management, your interrupt management, your prior, your inter-process communications. All these layers will come. Then your kernel will come, and then your hardware abstraction layer will come. Some form of layer that will not allow your kernel directly communicating to the hardware, and then your hardware comes, and then your these communication protocols comes. Okay, so this is how your Windows CE stack is there. So Windows CE it supports 4 GB of virtual memory. So if you don't know about virtual memory, just tell you virtual memory is like if you suppose there is two forms of memories. One is virtual memory and one is physical memory. Physical memory is like RAM. Suppose RAM is there. If you have 4 GB of RAM, that is means you have 4 GB of physical memory. Okay, if RAM is there 4 GB, that means you have 4 GB of physical memory. Now there is some hardware called MMU, memory management unit, comes into picture. Because what happens is, if I want to execute some applications, that application is large 4 GB, and if I want to run that, can I able to run that on 4 GB memory, physical memory, right? Because that is only 4 GB. Okay, and suppose if I want to run thousand of processes, 100 of processes I want to run, and all are like 500 MB or 1 GB, then is it possible to run all processes on RAM? No, right? Because we have how much physical RAM? We have only 4 GB of physical RAM. So we need to have some mechanism so that we can actually use that physical memory. So we what we did is, we are not going to directly touch your physical memory. Somebody should give some physical memory mapping, some physical memory location to us to execute there. Okay, so that work being done by your NMU. Your memory management unit is the hardware which is there between your CPU and your RAM. Then when your CPU generates some logical address, your virtual addresses, okay, when it generates some address, and it will ask your MMU, okay, can I access some data on this memory location? So your MMU is having some page to frame mapping. Your frames are the physical locations, your page are the logical memory locations. So if you have some mappings like page to frame mappings, then your MMU will do that thing. It will convert your virtual address to your physical address, and then you can directly access your physical RAM memory. So now what happens in this case is like, you can actually running in the RAM, another part of process running the RAM, you'll create some pages. If another process comes into picture, you will swap that page from your physical memory to their hard disk. Okay, hard disk is a backup kind of stuff, so swapping will be there. Okay, so some other process will be coming, space is left less, there is no memory to be executed in the RAM. MMU will decide, it will actually transfer your the page fault will be occurring. Actually, it will transfer your pages from your RAM which you are not using at that time. Okay, it will transfer to the hard disk, and which the pages which CPU wants to access, to load pages to the physical RAM. So that is how actually you are able to manage running different number of applications, different number of processes parallelly, and within the same 4 GB physical space. Even though if you have larger number of physical virtual logical addresses within the RAM, you can execute those things. Okay, so it's RAM, it supports ROM, that is read-only memory, and it also supports your flash memories. So yeah. So the ROM image footprint of OS, the footprint of OS will be actually you're installed within the RAM or ROM image only. That's a flash memory. A flash memory is nothing, it's a non-volatile memory. Non-volatile is like when power goes off also memory will be there. So that's the reason why we actually put our OS in ROM image, because when we want another when again if you power up the device, that OS should be there in the memory, right? If that OS will be not there, so that's why we used to put the OS in ROM image, some flash memory, some non-volatile memories. So OS is configured and customized for an embedded options, and your footprint is in the ROM image only here. for if you include the applications also, it will be like we need to optimize that to minimal to less than 1 MB of space. So this storage is just less than 1 MB. So with Windows CE with applications can be burned in ROM and configured as it is, does not allow end user extensions. This is ROM, what all RAMs we are using here. So you uses here in Windows CE we use persistent RAM also with flash memory also. But in case of Symbian we are only using, there is no persistent battery backed up RAM there case. Your memory manager here is a contiguous pages in virtual address space. I already told about what is virtual address space. So virtual address space and one is your physical address space. Virtual address space is being seen by your CPU. Okay, it can CPU cannot see your physical address space. That means the actual locations within the RAM it cannot see. CPU cannot see. So because there is abstraction called MMU, the hardware will take care of that. So it's a contiguous pages in virtual memory address space to one of the 32 memory slots, and the address space are allocated within the slots here. So it's a 32 MB slots. So yeah, so you can allocate some slots to some process. Like I'm slotting will be of 32 MB. Can run 32 content process here, like that. So yeah, so when you're using virtual memory concept, if you swap your pages from physical memory to your physical memory to your CPU and waste it down. Okay. So your will be fragmented. Then if another process comes of MB, then it can accommodate that within that space. But it is larger than 27 or 28. It cannot accommodate in that. So it will some other MB. That rest of the 27, 28 MB will waste. That's called memory fragmentation. So the memory management MMU also, the fragmentation also occurs in this case of memory virtual memory concepts. When you have process code less more than 32 MBs, process address space of more than 32 MBs. So it uses a dynamic heap in the program memory. Dynamic heap is like we have some kind of memories, like we have stack memory, we have heap memory. Heap memory is basically used for allocating the memory runtime. If any process wants some application or some memory, it will take it from the heap memory by using some like of malloc calls. In C library we have some malloc calls and we have some free calls. So by malloc we are allocating the memory at the dynamic at the runtime, at the runtime for the process, for the running process. And we can also free, if we will not free it, that memory will go waste, and because OS is not going to have the information because we have acquired that memory through malloc, but it is not, it is responsible are constraints with the memory leak within the application. You should be aware, developer should be aware that he need to free that memory, otherwise it's a problem of memory leak, and OS will never know about that somebody have taken the memory and he have not released that memory. Okay, so of process stacks, TCP, OS function stack, application, and OS functions and global variables, it's also supporting all those things. Wi-Fi stacks, Bluetooth stacks, it's supporting all those things. So yeah, so here this comes like cache. Cache is used but paging is not used. Processor cache is used along with the RAM and ROM flash memory. Now you may don't know what is cache. Okay, I'll tell you what is cache here. Yeah, so cache is like you have some cache. Suppose your CPU wants to access some data from RAM. So RAM is a controller, your dynamic RAM access that will be taking, you refreshing every time your RAM, and it will actually update your RAM for the data. Now it needs to sync up with the CPU, but it can't sync up because the CPU is running at different frequencies and DRAM is running at different frequencies. Now if some application wants to run, and if some applications wants to get some data, it have to wait otherwise, because DRAM is not able to get the data, right? So what we do is like we will do some kind of we will provide some mechanism so that we can reduce them, which we are taking to take the data from RAM, okay, which is very near to your CPU. So what will do your DRAM, what it will do, whenever CPU will execute for it will read, it will ask for some data, the nearby code, the nearby locations are also transferred to the cache memory. So another time it will execute another instruction that will be located in that space only, that memory region only. So the whole memory region will be capped into the cache memory. Okay, so those are called a store of memory regions. Like some space should be there in the cache. So that's, we have some data caches, instruction caches to store the data and to store the instructions, which are the operations and data on which we are operating the steps. So you will have two caches. One is data instructions, one is instruction caches, one is data caches. So process caches are being used to faster execution of your applications, because RAM it's not that much faster. Okay. Now paging here, I already told you, like paging means we take the, if some other application wants to use the physical address space, we are actually loading from physical address space to here hard disk. So it also supports for memory addresses, then built-in applications in storage memory, RAM. It also supports your process runs from XIP directly from process codes and data in ROM. This is not that much useful here. So ROM and RAM, OS and system functions in ROM. It supports your both ROM and RAM. It is supporting. It's actually okay, so for file system, it supports a file system with a root directory, which will be having some folders and file system tree. Okay. So at the top you will be having some root, and below that you will be having some directories. So it supports that kind of file systems. So division of file folders will be located in some regions. Okay. So each file will contain, each directory will contain some of the files. So file folders, we are actually giving it to the directories. So it supports your communication and network APIs, your serial, IRDA, TCP IP. These are the basic network APIs actually, so which all operating systems are supporting, like serial interfaces, your infrared, TCP IP, Bluetooth, and Wi-Fi stacks. For IP-based activity, they are also supporting Wi-Fi in the later versions of the Windows CE, and then smartphone softwares, or your cellulars, they are using GSM and CDMA technologies. Okay. For serial communications, generally for serial communications, we use RS-232 protocol. RS-232 protocol. And if you might have seen, you have some serial ports in your desktops. So those RS-232 port is like your D9 connectors. So D9 connectors, DV9 connectors, like you have 9 pins over there. Some pins are for receptions and some pins are for transmissions. Some pins are for configuring your status, your control data, and your some pins are for like ready to send, clear to send, like this. So there are 9 pins overall in the DB9. So that is your RS-232 protocol. Yeah. So it's for network connectivity. It also supports your LAN adapters. So LAN means it also supports your Ethernet. RJ45 is there. RJ45 is a port which is a 5 chip actually, which uses for your LAN devices, your local area network. If you want to connect your device, Windows CE, you can connect it. Windows CE device can be connected through Ethernet device, Ethernet on local area networks. So it supports your HTTP, HTTP protocol, FTP file transfer protocol, HTTP is hypertext transfer protocols. All these can be supported within this Windows CE. They are your UDP and TCP protocols. Okay, your UDP and TCP protocols are the transport layer protocols. So I'll tell you the network stack. So maybe in the next session, like Bluetooth and WAP Wi-Fi sessions, I'll be covering the whole network stacks. So at the lower level, we will having physical layer. Physical layer is like 5 layers. And then above that we will be having MAC layers. MAC layer is medium access control layers. Then above that we will be having our network layers. Network layers is managing your IP packets, and then above that we will be having your transport protocols. Transport protocols is like UDP, user datagram protocols, or your transmission control protocols. UDP is a unreliable protocols because we cannot get the acknowledgement. TCP is a connection oriented protocol, that is reliable protocol. Okay, so it's a transmission control protocol. So TCP and IP protocol suites, Windows CE supported that stuffs. So in depth we will be covering these networks in Bluetooth and Wi-Fi in the next sessions of these MOOC sessions. So it also supports some device drivers and also peripheral drivers for low level drivers to function at the kernel level. It also supports USB connectivity for the peripherals. Yeah. So now we will be coming how actually your Windows works. So Windows CE is a Windows CE is a mobile operating system. So from you have used your mobiles, right? How you use that mobile from your applications. When you touch something, some application, if you will touch your application, it will be running, right? But how it will run? So when you touch that application, then you are sending some interrupt signal. Okay, it's kind of you are sending some interrupt signal. Now OS is already having some interrupt service routines. Interrupt service routines are the functions which will be executed when any interrupt comes within the OS. Now interrupt are coming from the application, from user space, and when it comes, it will execute appropriate ISRs. Then that ISR, that interrupt service routine, will actually execute in the kernel space, and it will actually execute. It will provide you the function. It will provide you the feature which is implemented in the kernel space. Then it will send it to your user space. Okay, so this is how it actually works. So from application you will be getting some interrupt signal which being taken by your kernel, your OS. It will execute some ISRs, interrupt service routines, and then interrupt service routines will actually execute some of the applications, some of the features, and then the result will be sent to the user space again. So when built by the OS, it will start that application. So sends interrupt signal which is checked for source, that is whether the source is a hardware event or a software exceptions or a user based action event. The interrupt which I'm talking about is user action based event. If you are a user and if you are using something, you can also generate some events. Okay, events can be generated by your hardware also. If some hardware device is there, like suppose some network controller, some NIC, network interface card is there, and if you are receiving some packets from local area network and you want to give that packet to your kernel, to your OS, so that you can give that your packet to the application, you need to do some kind of mechanism. That will be your interrupt. You will be interrupting your CPU. CPU will take the data from NIC and transfer the data from NIC to memory, and then from memory to your application. Okay, so that is how your hardware interrupts actually works. So there is one hardware called your other device like USB controllers, like PCI controllers, like network interface card controllers, and then the interrupts is known by your CPU at the initialized time. Actually, they know all about interrupts, what all interrupts are associated with what all controllers. So when it gets some interrupts, it will see, okay, this USB controller is generating this interrupt and I have to execute this ISR routine, this interrupt service routine. Appropriate interrupt service routine will be called by that CPU, and then that functionality will be done. Okay, so we can generate hardware interrupts, we can generate software interrupts. Event handlers or interrupt service routine handlers, ISR routine. We can have synchronous and we can have asynchronous as well. So this is how actually it works. So when you are interrupting from your who will interrupt my hardware, like Epic programmer, interrupt programming controller will interrupt actually. So this will interrupt your OS kernel. OS kernel know if I'm getting this interrupt, I have to execute this interrupt service routine. It will, yeah. So it will execute that interrupt service routine. So executing that interrupt service routine, it will also run some application threads, because user wants something, right? So application threads will be running through the ISR only. So this is how your then application threads will give the data to the OS kernel, and then OS kernel will give the data to the user space. That is how so your Windows C is your event driven OS. Whenever user wants to do something, it will generate an event, your ISR will be called, then your application thread will be called, and then you're getting the data, you're getting your results within the application. So it's an event driven operating system which will be registering some interrupts. So interrupts will be notified to the OS, and for each request, I already told you, for each request there is an ISR assigned by the OS on notice. ISR is a short kernel code. I already told you about ISR is a small function which will be running in the kernel code, and which identifies your interrupt service threads. Interrupt service threads are the kernel threads which will be actually processing the service for the user space application, and then activates the IST corresponds to the request event. I think this should be clear for you. If anything is not understand, you are not able to understand this thing, let me know. I'll be covering this again, no problem. So this is how your external interrupts work with your user. Here we can actually provide the thread priority also. OS will also decide whether I need to handle suppose there are two applications running and I got two interrupts at a time. Now which ISR routine I need to execute first? So it will decide depending upon the priority of some other thread. It will execute the interrupt service routine of the first thread. So so that you are actually achieving a hard real-time functionality. So it's a hard real-time system with multiple processes running. If multiple processes running and they are executing and they are sending some interrupts to the CPU, CPU know which interrupt I need to handle when, because it knows about the priorities. So it's an event-driven priority-based kernel. Event-based priority-based kernel. We are with the help of interrupts and with the help of priorities, the kernel is able to find out which ISR it needs to run and which application code it needs to, application thread in the kernel it needs to run, so that it can provide the functionality of services to the users. Yeah. Any questions as of now? So we have 8 priority levels here. We have 8 priority levels. Highest priority level means time critical priority. If there is higher priority, we have time critical priority. That means we need to quickly run that ISR, because it's a time critical priority. So we can actually create real-time systems, because in real-time systems we can't wait. There is a very interrupt. The interrupt latency is fixed and very deterministic. Okay, quickly the result we want quickly and with deterministic time. We don't want any variations. So it will be in fixed amount of time we are getting that. So it's a hard real-time system. If we want to create, we can high priorities and we can create interrupts kind of stuff. So if priorities are same, each thread is allotted a time slot. Okay. Now what happens when if I have same priorities of the, if some process were there, so if we have time slots, I told you if we have different time slots, so in which mechanism we use time slots in the case of multitasking. If we have CPU time slots, that after that time slots we will be running that again another process which is having some another time slot of CPU. That is how we can actually manage if some two processes are having same priorities. Okay. So application development here we can do with platform builder, Visual Basic, and Visual C++, and then we can use platform builder's integrated environment here. And this is what the summary is all about here. There we are using memory managers like virtual memory concept I already told about, like how partitioning is done, like memory partitioning is done. File manager is the file systems for managing your files and directories on your hard disk to create the partitions, and then how your event handlers works, how your interrupt service threads, interrupt service routine works here. And then it also supports your communications and network APIs for serial IP, TCP/IP, Bluetooth, and stack and Wi-Fi stacks here. So IP-based mechanism, it also supports your Wi-Fi based networking connectivity, and yeah, Visual Basics, Visual C++, your application development. So this is the end of the part which was remaining from the last session, that is Windows CE. Now let me know, we have 2 or 3 minutes left over. The session is going to be over by the 10:30. So let me know if you have any questions, so I can answer those questions. So we'll be wrapping up this whole chapter with the Palm OS, Windows CE, and Symbian OS. We're covering this. Camera is already there, I think. Yeah. You have some sessions?
No. I'm just checking if everything is fine.
Yeah. I've completed.
The session is over.
10:30 is over now.
Okay. Just what you left the camera, so I was thinking how are you continuing? Okay. They had any questions?
Yeah, they're having some questions. If they have some questions, yeah. So IST is basically like your interrupt service threads. You have two things like yeah. I'm getting some questions. So no. So someone is asking about IST full form. IST is interrupt service threads. Like we have ISR, interrupt service routines. So like we have ISR, interrupt service routines, we are having interrupt service threads. So interrupts, after inter-service threads, we will be talking to your interrupt service routines. Okay, ISR is actually talking to your inter-service threads to manage your features. Yeah, somebody have already answered that in inter-service thread. Somebody is asking about Windows CE. Jntuk SO was asking about Windows CE full form. So I'm literally, as of now, I don't know about Windows CE. I don't know what is the full form of CE. So I can get back to you in the next sessions if someone can recognize me about that, or you can search on Google what is Windows CE full form. It's not a big deal. Any other questions related to your Windows CE concepts, interrupts, and your Symbian concepts, OS concepts? Okay, so I think it's already 10:30. So from 9 to 10:30, we already did. Our chapter is also completed. In next sessions, we'll be meeting you with the Bluetooth or maybe Wi-Fi stacks, whatever is remaining. And okay, thank you for your time and your patience to listening me. And yeah, if you have any questions, you can ask me. Otherwise, we can wrap up this.